time to pick up with nuclear chemistry and looking at what happens when alpha particles, beta particles, and gamma photons encounter matter. Okay? One of the first things that happens when alpha, beta, or gamma encounters matter is that it can impart energy. And when it imparts energy, okay, then it can create excited atoms or excited molecules, which increases the kinetic energy. And sometimes it can kick out electrons or break bonds, creating free radicals. Now remember, free radicals are atoms or particles that have an odd number of electrons. When you have free radicals then attack other molecules and can cause cascading damage. Okay? Ionizing energy is radiation that can impart enough energy to break bonds or remove electrons from individual atoms or molecules. Newly formed odd electron particles, free radicals, are very reactive and dangerous to other molecules around them and cause breakdown of other particles, and the damage multiplies. Okay. So, dangers of radioactivity for living tissue depend on half-life, okay, how long it's going to be producing particles, type of radiation, alpha, beta, gamma, biological behavior, the material that's going to be undergoing radioactive decay. How does it behave in the body? Does it get incorporated into some place important? Does the body slough it off quickly? Okay, an example is plutonium. Plutonium, when it's exposed to air, makes plutonium oxide. Very, very super fine powder. If you breathe in that powder, it actually becomes permanently embedded in your lungs, and then you have your lungs being continuously exposed to alpha particles and gamma radiation. Okay? If it's something that mimics calcium, so we know that calcium is an alkali earth metal, and since it's an alkali earth metal, strontium, radioactive strontium, can be incorporated in bones just like calcium can. Okay, so examples. Now, the doses for radiation are sometimes talked about in terms of RAM and REM, of the rads and REMs. A rad is a unit of energy absorption, and a REM is the unit of radiation dosage based on tissue damage. We're probably more interested in REMs than rads, talking about how it affects things biologically. Okay? Then we can talk about penetrating power. How far into tissue from the outside does a type of radiation go? Or, if it's inside, how far does it travel inside? So we're going to start with alpha particles. Alpha particles are the largest. Remember, there are 2 protons and 2 neutrons, and it has a 2+ charge. Alpha particles can penetrate to a depth of about 0.03 millimeters. Okay? They can be stopped by a sheet of paper because it strongly interacts with matter, because really in the grand scheme of things it's a large chunk. Okay? As an external source of radiation, not too bad. I wouldn't want to play with it, but not too bad. Internally it's very dangerous because of that really strong interaction. It'll do a whole lot of localized damage. Okay? Beta particles penetrate to a depth of about 2 millimeters. They go a lot further. Okay? And that's because they're much smaller. This is the size of an electron. Remember, a beta particle is a newly minted, very high energy electron. You need plexiglass and or double gloves to stop it. If you got a really heavy duty beta emitter, you often use mechanical devices to handle it behind a plexiglass shield. So as an external source of radiation, beta particles are more dangerous than alpha. They're less dangerous as an internal source because they're going to move out of the body much quicker. Okay? Lastly, gamma rays, no charge, no mass. It can penetrate into a depth of 10 centimeters. Okay? That's going to go all the way through your arm. It's going to make it over halfway in, penetrating from front to back to your body. It can move right on through. This makes it much more dangerous as an external source of radiation. You need lead or concrete to stop gamma rays. Now, it's not as harmful as the others as an internal source, and that's because 10 centimeters is the is the distance it wants to travel to get out. Most diagnostic radioactive tests are done with gamma emitters because they can detect those outside the body. You can't detect alpha particles outside the body because they're going to all be reacted with something else before they make it out. And beta is about the same way, okay, but they're spreading out a lot further. Now, let's look at a table. Remember earlier I told you that radiation is a part of your everyday life? Well, here are typical sources of radiation. We have cosmic radiation. We have radiation from the soil, from wooden houses, brick houses, cinder blocks, radiation in the air, radon. We can get it from X-rays. You get it from being near a nuclear power plant. A jet flight, which puts you higher up in the atmosphere, increases your dose of cosmic radiation. The average person receives about 100 to 200 millirems of radiation a year. Okay? You could sit and add yours up, go with the worst case scenario, what kind of house you live in, all kinds of things like that. But your dose should be between 1 and 200 millirems a year. Now, before you panic, that's okay. Your body is built to handle it. It's big doses of radiation that's so dangerous, okay? So if you have a big dose between 5 and 20 rems, you have the possibility of chromosomal damage, okay, which could lead to cancer. If you get between 20 and 100, you have a reduction in white blood cell count, and of course the possibility of cancer. 50 plus, if you're a man, that's temporary sterility. 100 plus, it's 1 year of sterility. Between 100 and 200, you have mild radiation sickness, that's vomiting, diarrhea, tiredness for a few hours, reduction in infection resistance because your white blood cell count is down, possible bone growth retardation in kids. Okay? The reason you have vomiting, diarrhea is because the cells along your digestive tract are some of the ones that are the quickest to overturn, to be replaced in your body. And those are the ones that experience the most damage from radiation. Okay, at 300 plus, women are permanently sterile. At 500 rems in a single dose, you have serious radiation sickness, you have damage to the marrow and intestines, and 50 to 70% of the population that receives that kind of dose will die within 30 days. 400 to 1,000, acute illness, early death, 60 to 95% die within 30 days. And at 3,000 plus, it's usually death within hours or days, 100% die within 200. Now, you don't go experimenting with radiation and people. So we've gotten all these things from things like nuclear accidents and Hiroshima and Nagasaki, which were not experiments in human exposure to radiation, but rather an act of war. Okay? So that's why we got some overlaps. This is not, super written in stone, but you get an idea. Now these are single doses, and notice that they're single doses in rims, not millirems over the course of a year. Now, before we say radiation bad, let's talk about uses for radiation. Radiation is used as a tracer to follow chemical pathways in the body or tissues. Okay? You can give something a radioactively labeled material and watch where it goes, or watch how it's broken down in the body or in tissues. You can use it to look at material flow, the flow of material through underground pipeways or water systems. We can use it a lot in medical diagnoses. Instead of kind of cutting you open and doing exploratory surgery and poking at things, they now can look at the function of your gallbladder, your liver, your heart, your kidneys, your thyroid through radioactive isotopes. And of course, it can be used to treat tumors. Okay? Now, a controversial use for radiation is radiation of food for preservation. Freaks a lot of people out. But the radiation doesn't stick to the food. If you were to vacuum seal something and then irradiate it, any bacteria that made it into the vacuum seal bag would be killed, and that preserves the food for a longer period of time. Okay? Now, nuclear transmutation. Nuclear transmutation is the induced change to the nucleus of the atom. Induced changes cause a conversion of one atom into another. Okay? So the splitting of the atom was a nuclear transmutation. This can lead to nuclei that are larger than the atom you start with. Every element past uranium was created through nuclear transmutation. Or we can split bigger atoms into smaller atoms. Okay? And they use what are called particle accelerators. The first transmutation was performed by Rutherford. Remember, he's the guy who found the nucleus. When an alpha particle emitted by radium was used to bombard nitrogen, and it created oxygen atoms. So nitrogen 14 plus an alpha particle gave us a proton and an oxygen atom. Okay? This is what led to the discovery of the neutron. All elements past uranium, as I've said earlier, are created by transmutation, as well as technetium. If you look at the periodic table at the front of our classroom next time you're in there, any element you see that's just outlined, it's not filled in black or filled in blue, is man-made through transmutation. And you'll notice technetium is outlined. We don't find any technetium, or we've never found it in nature. It's only been created in the lab. Okay, now here's some examples of some transmutations. Plutonium bombarded with helium gives us a americium plus a hydrogen plus 2 neutrons. Okay, plutonium plus helium can also be used to create californium and a neutron. And californium hit with helium can give us berkelium. And you can see down through there some examples of just transmutations. I want you to remember that the sum of the atomic numbers on both sides always have to be the same in a nuclear reaction, and the sum of the atomic mass numbers has to be the same. So notice 239 plus 4 is 243. And there's 240 plus 1, 241, and 2 times 1 is another 2, 243. Okay? Now, nuclear fusion. the splitting of atoms. In an attempt to synthesize elements larger than uranium, an interesting process was discovered. Fission. Fission is the splitting of an atom. A large atom like uranium-235 is bombarded with neutrons, and the atom splits into two daughter atoms. We actually know of evidence of a natural nuclear fission reactor. It was a uranium deposit that had a self-sustaining nuclear chain reaction. This was done, we found this by examining isotope ratios, and it was discovered in Okolo, Gabon, Africa, by a French physicist in 1972. The conditions under which a natural nuclear reactor could exist were predicted in 1956, and the conditions were found and predicted here. Okay? Now, there are no natural self-sustaining nuclear reactions going on now. That reactor is dormant. Okay? Happened about 1.7 billion years ago. So, the fissionable nucleus, uranium-235, is hit by a neutron. It creates an unstable uranium-236 nucleus, and it divides into a krypton and a barium. And it can give up to 3 neutrons plus energy. Okay? Our nuclear power plants are fission power plants. The energy given off there eventually shows up as heat. Now, when you look at the masses of everything after the fission and before a fission, you'll notice that the mass has changed just an infinitesimally small amount. And it goes back to Einstein's famous E=mc². A little bit of the mass of the atom has been converted into energy. We can harness that energy through a chain reaction. Now, in a chain reaction, one uranium is split and it gives off 3 neutrons, and a couple of those neutrons split other uraniums, which then split more uraniums, which split more uraniums. So you notice here it's going from 1 to 2 to 4, then it would go to 16, and it climbs very quickly. Whether a chain reaction occurs or not depends on the mass and the volume of the fissionable material. Okay? Because the neutrons from one step need to be there to split the neutrons from the next step, which will produce neutrons for the next step. Okay? A chain reaction to be useful to generate energy must be critical, which means it has to be self-sustaining. All fissionable or fissile isotopes undergo a small amount of spontaneous fission, which releases a few free neutrons into a sample of a nuclear fuel. So neutrons will escape, some neutrons would escape rapidly from the fuel and become a free neutron, which has a lifetime of about 15 minutes before it decays into a proton and a beta particle. However, neutrons almost inevitably impact and are absorbed by other nuclei in the vicinity before this happens. Okay? Some neutrons will impact fuel nuclei and induce further fission, some will not. If enough nuclear fuel is assembled in one place, or if the escaping neutrons are sufficiently contained, then freshly emitted neutrons outnumber the neutrons that escape from the assembly. A sustained nuclear chain reaction takes place. Okay? A critical assembly then is an assembly is almost entirely made up of nuclear fuel of critical mass. Critical refers to a cusp, which is a kind of equation. Okay? Now, the reaction reaction inside a nuclear power plant versus a reaction inside a nuclear bomb. Both of them have to have critical mass, okay, and have to have a sustained nuclear reaction. The big difference is in an atomic bomb, we have an uncontrolled chain reaction. Okay? A fission bomb, not to be confused with a fusion bomb, also called the atomic bomb or the A-bomb, is a fission reaction designed to liberate as much energy as possible as rapidly as possible. Okay? Development of the nuclear weapons was the motivation behind the research in nuclear fission, the Manhattan Project during World War II. I happen to have met a very nice man who was a professor at Indiana when I worked up there, who worked on the Manhattan Project as a graduate student during World War II. Very interesting man. Okay? He said that, you know, when they did the first nuclear reaction, kind of doing controlled reaction, they really didn't know what was going to happen. It was interesting. So we built 2 bombs out of the Manhattan Project, Little Boy and Fat Man, okay, that blew up over Hiroshima and Nagasaki. Nuclear bombs are set to detonate at a specific height, so you get maximum damage. Okay? The first fission bombs were thousands of times more explosive than a similarly sized chemical bomb. Little Boy weighed about 4 tons and had about 60 kilograms of nuclear fuel and yielded about 15 kilotons of TNT-like damage. Okay? So, in a nuclear power plant, we don't want to release all the energy rapidly. We want to release it slowly. So how you have the critical mass of material dispersed is different in a nuclear power plant than a nuclear bomb. Okay? So a nuclear bomb is designed to release this energy all at once. A nuclear generator or reactor is designed to generate a steady supply of useful power. While overheating of the reactor can lead to and has led to meltdown and steam explosions, the much lower uranium enrichment makes it impossible for a nuclear reactor to explode with the same destructive power as a nuclear weapon. Okay? It is really hard to extract energy and power from a nuclear bomb. Okay? So, I've embedded in here discussions on critical mass, okay, and how the fact that in a nuclear reactor, to control the critical mass, we have control rods. What the control rods do is they absorb neutrons, usually made out of boron or cadmium, and that limits the number of neutrons, which helps control the number of fissions that are going on at any given time. Okay, so up there where they've got them X'd out, those are neutrons that were absorbed. Okay, now here's a picture of Little Boy. I want you to notice that the uranium, okay, was split into 2 sections, so that you had subcritical mass. You don't want this sucker going off too early. So they had 2 separate masses that they brought together to create a supercritical mass. And they brought it together in a very short period of time. And then they had an initiator which gave a burst of neutrons that begins the chain reaction, and then the chain reaction becomes an uncontrolled chain reaction and you get an explosion. It actually has a TNT explosion back here that drives the two pieces of uranium together. Okay? Now, the speed of a neutron is about 10 million meters per second, or about 3% the speed of light. The complete bomb explodes in about 80 times 10 to the minus 8 seconds. Okay? This time is usually referred to as a shake. Now, there's the design of that boy. And it was a plutonium bomb. Okay? You had a polonium beryllium initiator, which is going to supply our neutrons, inside a hollowed out plutonium sphere, so you didn't have it in critical mass. Inside that was uranium-238, and outside was a conventional explosion, so that you collapsed that all in and compressed it, okay, and brought everything together, initiated the reaction. Woo! It was wild. So you had a fast explosive, a slow explosive, a detonator, and the detonation wave. The first atomic bomb used 33 pounds of that should be bomb. Used 33 pounds of 99.9% uranium-235. That was little boy. Okay? In a nuclear power plant, the uranium-235 is only about 1 or 2%. Now, critical fission reactions, a nuclear reactor. Okay? Devices that produce engineered but not self-sustaining nuclear fission reactions are subcritical fusion reactors. Such devices use radioactive decay and particle accelerators to trigger fission. So we can have all these different kinds of power plants, and it tells you what kind of fuels they're going to use. Now, remember, what's at the heart of a nuclear or atomic bomb is also at the heart of a nuclear power plant. Uranium-235 content in the fuel rods in a nuclear power plant is between 3 and 4%, whereas in an atomic bomb it's 99.9%. In the atomic bomb, everything gets concentrated into a small volume. In a nuclear power plant, fuel rods are spread out. Okay? The two things by themselves ensure being spread out and having a low percentage of uranium-235 that a nuclear power plant cannot undergo a nuclear explosion. Okay? So let's talk about the parts of a nuclear power plant. There are fuel rods. These are enriched pellets of uranium placed in steel or other alloy tubes. They're about the size of a pencil eraser. There's a moderator, which is used to slow the neutrons. Slower neutrons give better fission. By absorbing neutrons, you slow down the reaction. The nuclear moderator usually serves also as the coolant of the reactor. Water is most often used, or a water boric acid mixture. Control rods are rods made of boron or cadmium that absorb neutrons. The fewer the neutrons, the slower the chain reaction. So by moving rods in and out of the reactor, you can control the rate of fission. And the heart of the nuclear reactor is called the reactor core. If you look at this picture, this bullet-shaped building here, that's the reactor core. Okay? Now, at the heart of the reactor core, okay, that containment shell, and there's usually a double containment shell. This is 2 layers, okay? We have reactor rods, fuel rods, and then we have control rods. In the United States, there's usually 3 sets of control rods in a nuclear power plant. They're all on separate control systems, and they can be cranked in by hand, mechanically if need be. Okay? Now, this is a sealed system. The water and the moderator that's in here is trapped, and it's under pressure. Okay, it gets superheated and it goes through an exchange system, and it moves through another contained system where it boils water and creates steam. The steam passes through a turbine, and that turbine generates electricity. The steam is then condensed by another heat exchange unit, okay, and goes back. So this is contained, this is contained. This system right here is the only system that's open to the environment. Now, in this picture you don't see it, but oftentimes you'll see big cooling stacks. They look kind of like this. Ooh, they have that kind of shape. You can find those even with coal burning power plants, but that's that last heat exchange. Usually they try to build these plants near a body of water, so you've got a lot of water for this last heat exchange. Okay? But this is sealed, this is sealed, this is inside here. You can take a Boeing 747 and nosedive it into this sucker, and it's supposed to not crack. Okay, the big problem in Chernobyl, at that nuclear disaster, is they had their nuclear power core here in a regular building, not in a containment building. And if it's not in a containment building, if anything goes wrong in there, you can't contain it. Okay? So that was a problem. By the way, there's more radioactive material released into the environment from coal burning power plants than there are from nuclear power plants. Now, in recent history, we had a nuclear disaster in Japan because of a tsunami. Okay? The nuclear reactor, okay, power plant was built near the ocean. And the tsunami hit the generator, knocked out the generators that ran the pumps to cool off the reactor. And the nuclear fission was halted because the control rods were dropped in, but that doesn't mean it stops heating. There are all kinds of radioactive isotopes in there that continuously, spontaneously decay, and they produce heat. If you don't have coolant to take away this heat, the material inside the reactor melts. Okay, and once it melts, it's hard to control. They poisoned the reactor, which means they add things in so the reactor can never function as a nuclear reactor again. It can never undergo a chain reaction again. But you still got all this hot, molten, radioactive material. Okay? And you need to keep it cool because of those radioisotopes. There was an explosion. It was a hydrogen explosion, not a nuclear explosion. Okay? And they were having trouble with radioisotopes being leaked into the atmosphere and into the ocean. They're still trying to figure out how to completely control what's going on at Fukushima in Japan. I definitely wouldn't want to eat any bottom-dwelling fish living right off the coast of Fukushima. Now, let's talk about fusion. Okay? Fusion is when we take smaller atoms and we fuse them into larger atoms. The hydrogen bomb involves fusion. To initiate a hydrogen bomb, okay, you actually need an atomic bomb because you've got to get up to tremendous temperatures. Okay, so you take a hydrogen 2 called deuterium and a hydrogen 3, which is called tritium, and you fuse those together and you get helium and a neutron. Now, fusion would be a wonderful way to generate electricity. The only problem is the extremely high temperatures you need to create fusion. We're talking temperatures of the surface of the sun. No material can withstand these temperatures to contain the reaction. Right now, and for the last 20 years, they've been looking at magnetic containment systems and lasering as a way to initiate the reaction. So far, they've never been able to build a sustainable fusion reactor and have not been able to generate enough energy to even sustain production. So we're not there yet. During my scientific lifetime, they've always been saying it's 10 years out. That 10 years has never passed. Who knows? Maybe one day they'll get it. And if they do, whoever gets that will control the energy market. Okay, guys, that's the end of nuclear, and that is the end of the material for the semester. So go forth, study hard, do well on test 4.